But we got a really good presentation here for you today. Dr. Shane Underwood is going to give us some really good information about pavement engineering. Obviously, pavement engineering is not a new thing, but and there's important practice stuff related to that. But I know there's a lot of innovation that's been going on and important lessons learned. So it's definitely a good thing to revisit if it's something you haven't looked at in a long time. So I'm going to hand it off to him, and you'll be in good hands.
Thank you very much. All right, good afternoon, everybody. This is a good response. Much better than I had an 8:30 a.m. class this morning, and I said good morning, and I got crickets. So I just stood there for 5 minutes until somebody actually responded. Well, I appreciate the opportunity to come and talk to you all. I'm going to talk through some research work that we've done at NC State and the Pavements Lab. I don't know how familiar each of you are with those. I certainly know a couple of you are very familiar with the Asphalt Lab, but I want to give you just an overview of some work that we've done recently to give you an idea of the breadth, and then maybe give some ideas for discussion and kind of build on when we wrap up. I made sure when I put this presentation together to limit the number of equations that I included. So I've got, I think, 1 or 2 in here. So for some of you, you're dying for that slide, but I know others are dying to miss that. So, all right. So the talk today, I've got 4 things on kind of the agenda. I want to give everybody kind of an introduction to the Asphalt Multiscale Multiscale Characterization Lab. For some of you that aren't familiar with it, to kind of give you a sense of what that is, the scale of that, and so on. And then I broke the rest of the talk into focusing on 3 topics. We do a lot of research in the multiscale testing lab, evaluation lab, and I want to give you a flavor for the scope of what those are, and sort of at the end try to tie together on how it sort of all fits together at the end. So I will talk about one of the main things we do in the lab, which is deal with durability of pavement infrastructure, and doing that using testing and performance modeling. Then I want to talk about work we've done over the last 4 or 5 years on looking at functional characteristics of pavements, notably the friction and texture and safety aspects. And then something we worked on in the last couple of years, which is resilience to extreme events, notably hurricanes Florence, Matthew, and then most recently Helene. And then open it up for questions. Okay, so what is the Multiscale Mechanics and Characterization Lab? We do research to try to understand how material behaviors affect long-term performance of infrastructure elements, notably pavements and roads. We've got a number of labs throughout the multiscale testing lab. When we moved into the new Fitzwillard Hall, we expanded the labs and organized some of the characteristics. We've got about 7,500 square feet of space where we do all kinds of characterization and evaluation of asphalt mixtures. This is just one example of a kind of test that we do to look at cracking or fatigue behaviors. The basic tenet of our approach is to look at the fundamental characterization of materials, to understand what those cause and effect relationships are across scales, not only on the asphalt mixture as a whole, but also on the interactions between asphalt binder and its interaction with aggregates, how that affects durability in terms of cracking, permanent deformation behaviors, moisture resistance, oxidation, aging, and so on. And that's really our approach, is thinking about this mechanistically and thinking about the scales that exist across that. Now, we do a lot of focus on function or structural characterization of materials, but we also do evaluations on functional characterization. So we have equipment and facilities to look at things like pavement surface texture. We collaborate with outside parties to look at pavement friction at full scale, and so on. The principal investigators in the lab, so I am one of 3 investigators in the lab. The lab itself, the Asphalt Lab, has been in place since, I think, in kind of its main form since the 1980s. Over the last 20 years or so, we've pivoted to more of a focus on multiscale characterization and the application of mechanics. But there are 3 of us that do research in this lab, and we generally focus on different aspects of that scale. You can see the other PIs listed. Dr. Cassie Castorena looks at a lot of the asphalt binder scale characteristics, how the binding material behaves, as well as preservation of roadways and recycling. Dr. Richard Kim is the senior faculty in the lab. He does a lot of research on asphalt mixture behaviors, and then looking at how we use performance predictions to look at quality assurance, production and design. And then I kind of stand in the middle. I do work a little bit on the binder side, but a lot on the scanning or spanning between asphalt binder properties to asphalt mix. So my job is really the intermediate scale. And then we also look at pavement resilience and the pavement functionality. The lab is highly supported by the local Department of Transportation. They're probably our biggest funding agency in the lab. But we do work for other states. We also do work for federal highways, private entities, and so on. All right, with that sort of overarching introduction, I want to talk about the first topic, which is pavement durability and structural performance modeling for asphalt concrete pavements. So I think everybody in the room knows, but I think the unique aspect of pavement engineering is the heavy focus on engineering to fail. In a more careful way, that's saying we really want to pay a lot of attention to the controlled, managed deterioration of the asset and engineer and design that asset with that controlled deterioration in mind. I think more so than we often do in other assets. And I think one of the reasons is because the risk of premature failures in terms of loss of life and damage to society is much lower, which gives us, I think, a reason to engineer at a certain margin when it comes to structural design and management. But the caveat in that is that in order to do a better job of engineering at that margin, we really need a way to understand how external factors affect a given and specific asset. And those external factors include traffic conditions, weights and types of vehicles, the climate or the weather patterns that manifest at a given location, the material properties that are embedded in that specific asset, as well as the foundational properties that exist. And so we have a lot of physical factors that contribute to this deterioration of pavements. And our goal in doing a lot of the work that we do is to try to model and predict the interaction between those physical mechanisms in as accurate a way as possible so that, again, we can hopefully get a reasonable prediction of how that deterioration will happen and then make more economical and efficient decisions on how we design things. So our focus is on those improving our reliability of predictions of performance. Now, the system that's been developed at NC State over several years, we call it a PassFlex system. We have to name it something, and PASS seems to make sense, and we're dealing with flexible asphalt concrete pavements. And so we've created this system consisting of three primary components. I'm going to go through these components as I continue through the presentation. But these components in this system is trying to look at the major ways that pavements deteriorate, notably fatigue cracking that occurs in pavements over time, and in combination with load repetitions, oxidation from exposure to the elements, as well as moisture damage and other physical factors that are causing deterioration, as well as rutting characteristics. These are the two main failure mechanisms and pathways we look at for flexible pavements, at least in North Carolina. We look across the U.S., especially in cold climate regions. Then we might look at also thermal cracking, which the PassFlex system does look at, although the model hasn't been validated as thoroughly as the fatigue cracking and rutting. And again, sitting on top of all this while we're thinking about load effects and climate effects are the impacts from consistent deterioration just due to normal oxidative aging and moisture damage characteristics. The first component of the system is labeled here as AMPT. That stands for Asphalt Mixture Performance Tester. It was actually named when it first came out as the Simple Performance Tester, and they tried to put it into production labs, and they realized it wasn't so simple. So it was remarketed as an Asphalt Mixture Performance Tester. At NC State, we've been pretty instrumental not in the hardware development of the instrument, but in developing the test methods and the procedures and the standardized protocols that are used to evaluate the properties of the material. Our main contribution exists in three domains. One is in identifying means to characterize the modulus of the material. Complicating matters in asphalt concrete, as many of you know, is that the material is temperature dependent, but also frequency dependent. And so we've devised methods, standardized methods to both measure the data and also analyze it in ways that are amenable to pavement performance prediction inputs. And so we use these temperature and loading effects to understand how the pavement responds under a prescribed load level or axle configuration and external factors. The second big contribution that we've made in this is looking at fatigue behavior. Now, fatigue behavior characterization in asphalt concrete has gone through a number of stages over time. Probably considered to be the gold standard of this is that we make a beam and we flex that for a number of times until it fails. Where we've stepped in to try to provide new context in this is simplifying the test procedure for one, but also developing a theory based on continuum damage mechanics to try to characterize that material. And what that does effectively is simplifies the characterization and limits the number of highly empirical tests that we need to run. In a practical sense, it takes the need to run 20 or 30 tests down to the need to just run 3, because what we're trying to get at are the fundamental characteristics of the material. If we understand those fundamental characteristics, then we can understand the effective externalities in a much clearer way. And the third contribution is in looking at permanent strain accumulation. Now, in this case, we've defined some phenomenological theories and extensive characterization of the material to develop a method to characterize the material, the asphalt concrete, and then we can leverage that in the prediction algorithms to predict how pavements are going to rut over time, which again is a critical failure criteria to think about. Now, a lot of our analysis and methods are actually quite complicated. So one of the big things that we've done in recent years is simplify that quite a bit by creating a number of tools that are available to departments of transportation, to companies, which are usually the main users of some of these tools at the moment, and other partners that can analyze the advanced theories that we're creating in a simplified way. And that's what the second component of the system is. So FlexMat is a tool. It's freely available. We worked in collaboration with Federal Highway Administration to create this tool. A user runs the experiments according to the standardized protocols that are developed, and these are standardized by ASHTO, and then uses this tool to analyze the fundamental characteristics and to provide input for the third step. This is another schematic of that for cracking, just to give you an idea. Again, our focus in a lot of the practical aspects of this work are creating standards that are standardized by agencies, in this case, ASHTO. And then the FlexMat tool does all the heavy lifting with respect to theory and analysis to provide fundamental behaviors related to the linear viscoelasticity of the mixture, as well as the cracking potential of the mixture. And I'm not getting into all the details. Remember, I told you I was going to spare you the equations today, but we use this again to generalize across a number of external temperatures, loading conditions, and so on, and then devise some practical tools that can be leveraged to understand the material. The final component of the PassFlex system is, we call it FlexPave. You can see the consistent use of flex there. Again, we're not very creative when it comes to naming things, but the basic idea there is flexible pavements. And this is a pavement structural performance assessment tool. It takes material inputs from the various models that are characterized in the FlexMat tool, does 2 steps. We identify the structural response of the pavement, what the stresses and strains are inside the pavement structure as a function of the loading and foundation conditions, and then leveraging the models that we created predict cracking, rutting, and actual in-service condition as a function of time. And I'll show you some examples of how we leverage that, do some practical things. So again, this is just another slide to kind of give you a snapshot of what is that FlexPave tool. It's a performance prediction algorithm. We talk about trying to engineer materials to fail, that controlled deterioration. A big part of that is understanding what's the damage or cracking going to look like over time, what's the rutting going to look like over time, and then making design decisions based on it. So the tool takes necessary inputs, structural layout of the pavement, the climate data, so what's the weather look like, predicted weather look like over the next 30 years, basic traffic information, how many trucks, how heavy, and then it predicts stresses, strains, damage or cracking, and then rut depth over time for this. So I'll give you an example of how this might be used. This is an example from a project we've done with Virginia Transportation Research Council and Virginia DOT. And the pictures that you see on here we call them damage contours. We try to make them easy to understand. Red is bad, blue is good. Areas that are red are predicted to have a lot of damage accumulation under the action of the loading. Areas that are blue and deeper blue have less damage over time. And then as you run from your left to right on this, it's different snapshots at different points in time. So 7.5 years up to 30 years. And if we just look at one row, you can see that we can visualize how damage is growing over time. And clearly in this case, we see a lot of damage at the bottom of the pavement owing to the bending nature of loading. But we also see damage at the top of the pavement owing to temperature variations, but also shear stresses and strains that manifest at the top of that pavement. And in the intermediate layer, again, we see very little damage, again, because of the balance between where the loads are and the material properties. Now, in this particular image, I'm showing you two rows of data. Each corresponds to a different mixture. So this is just a snapshot example of how these tools are used to evaluate and rate different material options that may be used on a given pavement structure. Now, the one at the bottom that says mix D3 it's labeled BMD, and I'm not getting into it here, but one of the recent evolutions in pavement material selection is called balanced mix design, and it's essentially integrating performance testing into the decision making on composition. And that mixture on the bottom has been engineered to a higher degree than the one on the top. And specifically, what's been done is that we've used what's called a recycling agent or rejuvenating admixture into the mixture. We've also lowered the binder content to make it a little softer, which helps to facilitate fatigue damage resistance. The one on the top is a control mixture. That is, again, a normal mixture by normal design features. It doesn't have that engineering embedded into the mix design. And what we do with this tool is see what's the actual benefit of that. And we can leverage this to look at not only the cracking evolution, but what needs to happen in terms of damage repair in the future, what's the cost of that going to be, and then doing some engineering assessment to figure out which one may be more efficient to use. We do look at this in a couple of different ways. So this is the same data. Here I'm just plotting it as a temporal variation. So I was showing snapshots before. And on the left, it's indication for the conventional mix. And on the right, it's that balanced mix design engineered to a higher degree. And what we see from this is the new mixture, the engineered mixture, where it's placed, which is only on the top, has a much lower damage level than the top mixture. But there's always a trade-off. In pavement engineering, as many of you know, we talk a lot about pendulums and we talk about balancing. And in our case, we're balancing cracking with permanent deformation or rutting. So the FlexPave tool, to be comprehensive, doesn't just look at cracking, it also looks at rutting characteristics. And the trade-off in these two mixtures is that rutting. So you can actually see here we've got the D3 mixture on the right, the D1 mixture on the left. And in the case of the D3 mixture, we're getting more rutting predicted. Okay. What we are able to do with the prediction of these properties is make a comparison and evaluation of whether we're okay with that difference in performance. Okay. And normally in our case, we're really paying attention to total rutting around 1/4 of an inch. So if we were to look at this, we might say, yeah, we might be okay with this balance. Okay. The tool allows us to make that prediction and then make that decision. Instead of relying solely on material characteristics, we integrate where the material is going to be used and think about the structural implications of those materials. Yeah, please.
Are these data points mathematically calculated or laboratory data?
Good. The 2 points you see here are mathematically calculated on the basis of material data. So that doesn't really answer, that kind of gives you a no answer, right? So what we do is we test these two materials, we obtain their properties, and then we feed those properties into the structural modeling and the theory to predict what the in-service rutting and cracking are going to be. And so what we're seeing from this is, given the same structural configuration, the same loading configuration, mix D3 with all of its engineered properties is not going to perform as well in rutting, but it looks like it's going to look better in fatigue. And then we can do some more rational decision-making on balancing. I'll show you one more example. This is an example from North Carolina where we were tasked to look at the possible benefits of incorporating fibers into asphalt mixture. In this case, we were looking at damage, and when you look at the contours on the top, you can see that the mixture with the fiber, especially for the benefit of those that are online, if you look especially at this area here, we have a lot less damage extent than we do here. And that's because this top layer of asphalt in this pavement is fiber modified. In this pavement is fiber modified, which gives us some benefit. In this particular case, this is not a selling fiber modified asphalt. Just to give you an example of the kinds of comparisons that can be done to evaluate the effectiveness of different material design technologies in balance with structural design and use case. Now, the tool itself has been validated pretty extensively. This is just pins for the locations where full-scale pavements have been constructed and then used to validate the model in many sites in the US, but also sites internationally as well. And this has been validated for a number of materials, and I'll show you just the correlation that we see that we can actually do this to predict. One of the things that we run into in pavement engineering, and I think a lot of computer-aided engineering, is we can get a number. That's pretty easy actually to do, but figuring out that the number means anything in the real world. And that's one of the things that we've, especially Professor Kim, has focused on in the last 5 to 10 years, is making sure to develop those correlations and demonstrate that it actually can match what we see in the field. The second topic area I want to go over deals with pavement safety through friction and macro texture characterization. Now, the connection between pavements and safety is skid resistance. And that skid resistance arises from a couple of different mechanisms. When your tire rolls over the pavement, it's deforming, and that deformation is dissipating energy, and that helps to give you traction. And the other thing that we get is adhesion between the tire as it rolls across the pavement. A contributing factor to this surface friction and texture, first surface friction, is the amount of texture that we see on the asphalt concrete. Higher texture, especially what we refer to as macro texture, which is the texture that we see with our eyes. Think about wavelengths anywhere from 0.5 millimeter to about 20 to 50 millimeters, so around an inch or two. We see as macro texture, and that macro texture helps to do a lot of things. It helps to deform the tire as it's rolling. It also helps to collect water in wet conditions and reduce or increase the effectiveness of tires. And so we've looked extensively over the last about 5 years at the interplay between skid resistance, surface texture, and surface friction. Now, contrary to the previous study I showed, this study has been an extensive field effort where we've collected friction and texture data. I'm not going to stand here and count them all, but it's about 300 pavements here in North Carolina and Virginia. The Virginia ones aren't shown, where we've collected real in-service high-speed laser texture data as well as friction data. That's been, we don't have the equipment to do that. We work with KPR Engineering, who actually does the in-service friction, continuous friction and texture testing. And we look at things like what's the effectiveness of different surface types in North Carolina and elsewhere. And each one of these corresponds to a different pavement texture. What's labeled as dense is the traditional mix that you would encounter and probably drive on the vast majority of the time. What's labeled as OGFC, maybe I should run an experiment. Who knows what OGFC means? Oh, one. Yeah. Open graded friction course. Yep, open graded friction course. Lots of negative macro texture. If you've ever driven on US 1 south towards Sanford, you've driven over it. If you've ever driven in the rain, you really appreciate it because it lowers the amount of splash and spray that you see. UTBWC, anybody know that one? Same, what is it? There we go, ultra thin bonded wearing course, a positive macro texture. And what we see labeled here is, as I should have described that, MPD is mean profile depth. It's a measure of macro texture. The higher that number, the greater the macro texture. And then we've got other surfaces that we see here. And what we learned from this is that dense graded mixes in North Carolina have a fairly low texture. That has implications when we start thinking about crash rates, when we start thinking about skid resistance, and so on. Beyond collecting data, we've worked to develop friction models to identify how long it takes for the friction to be regenerated after an overlay. One of the things we learned quite early in our evaluation is that friction can drop after an overlay. I don't think that's entirely surprising to anyone, especially if you've driven on a recently overlaid pavement. I myself feel a little uneasy when I'm doing that. No other reason than it's very shiny and it feels slick. I don't know how to describe it other than it feels like I should be scared to drive on this a little bit. And so we've worked on data-driven models to try to understand how that evolves and try to flag how long will that process last before we start to see maximum texture built and friction. Here I'm showing friction modeling, but we've done the same thing with texture. And as you can see, there's a lot of variation in this data, a lot of variation in real world friction and texture data. One of the biggest questions that we've trying to get in an understanding on is, well, okay, so I talked earlier about asphalt concrete mixture behaviors, but how do those compositional factors contribute to things like safety and texture and friction performance? And so we've spent a lot of time looking at, again, from field data and lab data, what are the contributing factors to giving good or positive macro texture characteristics? And I'll show you a couple of examples. So here's an example where we're trying to understand what are the volumetric factors that lead to texture increases. And texture is important, as I'll show you in a few minutes. It relates to crash rates. And so having good texture on a pavement helps to reduce wet crashes, which is one thing that we want to do as pavement engineers. Right? We don't just think about the cracking and rutting, thinking about safety. And here's a case where, again, we're predicting MPD for our equation lovers. This is for you. We're just doing a regression equation. It's pretty basic stuff, but it provides a lot of useful insight. We learned from this that having a lot of asphalt in the mixture helps reduces texture. We also learned that having fine graded mixes like we use here in North Carolina results in low macro texture, and having high asphalt content. I've already said deals with high macro texture. We look at the same in friction. Again, what do we learn? We learn that composition matters when it comes to friction. It is not the only factor at play, but it's one of many factors that is quite important to dictating the frictional characteristics of materials. We are very fortunate in North Carolina from a pavement perspective that we have very good high quality aggregates that don't polish very often. Generally speaking, our micro texture of aggregates is fairly uniform across the state, although there are areas in the Charlotte region which have very, very high micro texture materials. But again, we find relationships between composition and friction with respect to how much fine material, how coarse or fine the gradation is, and how much asphalt. So what do we learn from these characteristics and these investigations? We learn that to generate good friction and texture, we really should be thinking about the gradation. Is it fine graded? Is it coarse? And this is what it looks like in a lab setting when you have a fine graded mix versus a coarse graded mix. When it's paved in the field, it looks a little different, but still visibly different to you, and certainly different to the amount of water pressure that builds up underneath your tire and the pavement when it gets wet. We also learned, not unexpectedly, that binder content. Put more binder in the mixture, we lose texture, we lose friction, especially friction. And then how much filler we add. All of that matters. The filler actually is an interesting interplay because there, as we have more filler, we generate tougher mastic films, and we affect how that wears off over time. We know just from living in North Carolina, pavements start very black and they become gray somewhat quickly as the film gets worn off. And having a tough mastic affects that wear off. But as I said, the goal is not just to understand how texture and friction arise, but it's really to understand how this affects safety. And so we couple this analysis with analyses of crash rates. In our case, we're really focusing heavily on high-speed facilities because that's where we tend to see many issues. And we also look at wet crash rates. What happens when it actually rains? And you can see that as you imagine, there are a lot of factors that contributes to a crash. But we do see relationships. We see that when the friction gets very low, that crash rates increase. It's one of many contributing factors, not the only factor. But when we look at the graph on the left, you can see that crash rates are fairly stable to a point, but below some friction level, those crash rates start to increase. And what does that tell us? It tells us that it tells us that friction is having a contributing effect here. And that's what we want to avoid. I don't think with surface characteristics we eliminate crashes, but we can certainly affect a contributing factor in some cases. And so one of the things that we've done recently with the NCDOT is analyze a number of those 300 sections that I talked about to find out where is that inflection point happening? Where do we see crash rates increasing as a function of texture and friction? and propose some initial, at least, threshold values for them to think about. And again, in this case, we look at other contributing factors like demand for friction and texture, which is going to be higher in interchanges and around curves, and we adjust based on it. And here we propose investigatory and intervention thresholds, cases where maybe let's take a closer look, friction may be combining to crash rates, and one where we have pretty strong evidence that it is, whether or not it collected in small areas. Okay, the third topic that I want to talk about here is resilience to extreme events. I know I'm going around because I want to give you all a cross-sectional feel of what's going on. So when we talk about resilience to extreme events, we recognize that North Carolina has an incredibly diverse and dynamic climate. There are a number of weather-related stressors that impact and affect our infrastructure. And I'm showing some of them here. It's not just hurricanes that impact our infrastructure, wildfires, extreme precipitation events, not necessarily associated with a hurricane, tornadoes, droughts. All of these have fingers that touch pavements. You might ask yourself, how in the world does a tornado affect a pavement? And you're right, it doesn't directly affect a pavement, but certainly the cleanup affects it. The removal of debris, the transport of debris is going to happen over a pavement. Some of these are multi-physical impacts. Fires can, and there are evidence of it burning a pavement, but more so it's creating situations where we could have more debris flows from later precipitations that could impact pavements, and so on and so on. We focused heavily on the question related to flooding, and more specifically, flooding related to hurricanes in eastern North Carolina. We've looked very carefully at Florence and Matthew impacts, and with the plan to look at Helene in the near future. But when we look at flooding impacts, we can break them down into two broad classifications: things that are immediately apparent and things that are not immediate. Immediately apparent are pavements washed out, shoulders are washed away, those sort of things. Pipes are gone. These are the sort of things that become readily apparent that damage has happened. And the immediate acute response to that is pretty clear. We need to open for traffic, for mobility. Let's repair that right away. In our opinion, the more dangerous or the more worrisome damage is the one that doesn't show up immediately. It's the one that's brought on by the fact that we're moving high weights of goods and services around. It's the one that manifests because the foundation of the pavement has been inundated. It's the one that we're dealing with in eastern North Carolina, military-related vehicles using the roadways for evacuation and disaster support. Those are the ones that we really, in our lab at least, we feel like we have something to say. And so, the basic impact from flooding is in stress distribution. No equations, but concepts. Flexible pavements especially work to distribute the loads over larger and larger areas, and we build up structure to do that. When pavements are flooded, especially the foundations are flooded, those soils are saturated, it weakens the foundation, which exacerbates the impacts of loads and accelerates the deterioration that may occur as a result. And this is the basic pathway for damage to happen in this case, and that's what we're trying to understand. So if we look at it, in a broad sense, if we look at pavement deterioration, I talked about controlled deterioration. This is what we would expect from a pavement. If we have a major flood event, different things can happen. The pavement could deteriorate very rapidly after that event. The inundation is severe and the loading is serious. More than likely, what we're going to find is an earlier failure that's not readily apparent. It's actually going to happen over 5, 10, 15 years, that we've consumed a number of the amount of life of that pavement due to the particular instances of loading and configuration. Okay? So there are different kinds of effects from inundation. That picture, I think, does anybody know where that picture's from? I-40, yeah, I-40 following Florence in eastern North Carolina. Everybody in here knows where it's at. When I go out of this state and I start talking to people, they tell me it's a really nice river we've got here. I have to say, no, that's not exactly what that is. So how do we look at these immediate impacts? Well, there are a couple of ways that we've been championing to do this. One is a strong statistical-based, data-driven approach, and the other is a mechanistic-based approach. I'm going to show you a snapshot of both. So when we think about data-driven approaches, what we try to leverage are the expected deterioration of pavements, which we can identify through analyzing pavement performance data that's collected by the DOT on an annual or semi-annual basis. And this flowchart is kind of giving you that idea. So a bunch of data is collected on normal deterioration pathways. We look at how that's uncertain. Big characteristic of pavements is that the performance is uncertain. And that's what you see in the middle picture. These are a collection of pavements under a given cluster and how they perform, bounding what their uncertainty band is, and then looking at, well, how do pavements that have been inundated respond given that uncertainty? Can we actually parse out from all of this data that, yes, in fact, the pavement is deteriorating more rapidly? And that's what we've done. And we do that in a couple of ways, but I want to jump to an example of where we've done that relevant to the image that I showed you in the preceding slide. So this is that section of I-40 that was flooded. In the bottom graph there, we've divided this into three sections. It's going to be a little confusing, but one of these is westerly, even though it looks northernly. Okay. The other is east. So we've got the west section, the east section, and the central section. If that really bugs your eyes, you can go north-south. There's no harm in that. In the bottom, we've got the expected performance from that given historical pavements in eastern North Carolina that are interstates and are major routes and have high traffic volumes. And then plotted on top of those are the points indicating how the pavement was performing before the flood happened, in the year before the flood, and in the years following it. And an interesting thing really emerged from this. One of the things you see in the central region, before the flood, the pavement was doing good. It was actually at the 98th percentile of pavements of similar age and class. And after the flooding, it maintained that. There was little damage that had happened. If we look at the eastern branch, the yellow color here, it was at that 98th percentile, but then after the storm, it fell below the 50th percentile. So are there pavements at its age that look the same as this does after the flood? Yeah. But it's odd to see a pavement go from really well performing to now being less than average in the location. And then when we look at the far easterly section, you can see that the year after the flood, it actually had deteriorated quite a bit. Turns out that there was a rehabilitation done in the year. The point of this is that it is feasible to identify locations where the damage is happening, but it requires a much more nuanced and higher data-driven approach than we would normally. The more localized approach is to leverage those performance prediction tools. Again, when I talked about FlexPave and FlexMat and all of that at the front, it's all about integrating the multiple sources or the multiple physics that affect pavement performance into a prediction model. And one of those behaviors is soil properties. What is the foundation property of that material? And so we bring to bear these FlexPave tools to collect things related to the weather patterns, the materials we use, the structures that are in place, the traffic that is being used. And we feed all of that in addition to the flooding impacts into the pavement performance prediction to identify how distresses may accumulate under the action of flood and identify locations that may be subject or design conditions that may exacerbate or mitigate that effect. One of the things we do to do that is try to estimate how water moves through the pavement surface. So we use modeling to try to estimate. You can see this is a C2D model, if those of you that may know about this. And we can actually simulate an inundation on that pavement surface and identify how this water moves through the soil. And on the right-hand side is sort of a profile of what that saturation looks like as a function of time and as a function of the inundation that we have. Okay, and we can actually get reasonable predictions of inundation, and then leveraging physical relationships between degree of saturation and flooding, we can start to look at what's the impact on the modulus or the sparing capacity of the soil underneath the pavement, and then integrate that into the long-term performance predictions. And so the graphs here are showing just an example of what might happen, be predicted to happen to the foundation under a flooding event. We would have been high. We obviously see seasonal variation in resilient modulus. We would have expected during this season the modulus to be here, but because of the flooding, we had a period of time where the foundation was weaker than it otherwise would have been. In this case, we're looking at the aggregate base underneath that pavement and then the subgrade soil below that. And we can see what the implications of that are on performance. Again, to identify, quantify what the potential impacts of flooding are in a given location situation. So on the left, you can see the expected performance over time with no flooding. And again, this is analytical prediction or a computational prediction of the rutting based on the specific material properties that we have, including the foundation layers. And then on the right, what happens under a 3-flood case. One of the challenges with trying to do this forecasting is estimating what's the flooding scenario going to be like. And so the approach that we've taken is this scenario-based approach where we hypothesize different flooding frequencies to see what the impacts are. And one of the things we learn is that flooding that happens early on in the pavement life has a much more of a larger effect than flooding that may happen later on in the pavement. And you can see that in this particular image, the vertical gray lines are the timing of the flood. So there's a flood here, 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 and clearly we see a big increment and big jump in rutting that occurs due to that first flood. But it continues, and in this case, again, we see the predicted rutting is higher. Whether that's significant enough to reduce the life, again, depends on the exact sequence of those floods and the particular characteristics of the pavement. That was looking at rutting. We also look at damage. Here, the contours aren't quite as fancy looking, but it's the same idea. Red is bad, kind of blue is better, green is better. The colors on the screen are a little bit washed out. But again, what you look at is the timing of flooding and the frequency of flooding and the amount of damage that's existing across the pavement section. And clearly, if we look along this bottom row, if we have more floods and they're distributed at the early, mid, and late stages, we see a lot more damage occurring, okay? The difference between the top and the bottom is the subgrade, right? Sand subgrade drains water, doesn't hold it very long. And so that recovery process in the subgrade resilient modulus is much faster. And therefore, the long-term impacts are much.
What is the X scale measurement?
Thank you. Yeah, so the X scale is the cross-section of the pavement. So you're looking at a pavement cross-section, and you should imagine in this that there is a tire, basically, right here, coming out of that page. So the extent of the tire is probably, in this case, probably something like this. And then as it distributes, the reason you see that load, that damage at wider widths is being distributed over the pavement.
Along the profile of the tire traveling in the X direction.
Correct. And the Y is the depth of that concrete layer, asphalt concrete layer. Yeah, so it's kind of coming right out of the page ends. Apologize that I didn't make that clear. Okay, so with that, I'm gonna wrap up. And actually, pretty good. I have to give myself a little pat on the back. An academic was told talk for 45 minutes, and I went 47. So I feel pretty good about this. So if I want to kind of wrap up and say, well, okay, so I tried to give you a snapshot of 3 things. This is a busy diagram, and it's mainly here to just let me talk through it. And if you don't want to hear me, you can kind of read it along. Big theme in our work is to try to integrate mechanistic analysis into the process of pavement engineering. Now, the process of pavement engineering spans a number of things. There's the design of the material, the design of the structure itself, the construction of that asset, and then the management of the asset over time. And right now, those processes are largely separated. We do mixed design under one set of rules with a tacit understanding that it's going to impact performance. We then engineer the pavement in one way, but we don't, unlike what we do in many other structures, we don't necessarily explicitly take the material properties and plug that into the design. Part of it is because of timing, right? We're designing pavement structures 2-3 years before we're actually selecting a contractor. One of the themes for using these mechanistic approaches is to try to tie that together more explicitly. Not only in terms of designing materials and designing materials in conjunction with the structures that we're trying to use those materials in, but also helping to manage them in the long run. We talked about extreme event impacts to pavements and how that's uncertain and how we don't know what the long-term effects are. But what we do have the ability to do is, now that a pavement has been flooded, to predict what is the likely impact. How long do we have before our pavements are going to start failing? And we can plan for them in a way that we can't do with data-driven approaches. We can actually project to say, okay, the pavement is expected to start to deteriorate more rapidly. So instead of planning for overlay in 10 years, let's start to plan for one in 5 or 8, because it's going to be needed at that time. By integrating those tools, we're able to, we think, create a more cohesive structure that, again, allows us to engineer at that continued or managed deterioration process a little bit more carefully. Okay, with that, okay, I lied, 12:49, so I ended 5 minutes late. I'm going to count that as a win. Thank you very much for your attention. I'm happy to talk more about it.
Safety from person perspective, is there a consideration of higher noise?
Yeah, I'm going to repeat that a little bit so the folks online can hear. So the basic question was whether we consider noise in this. We don't, but it is considered. One of the examples of that would be the OGFC, the open graded friction course that we were talking about. In some locations, one that comes to mind is Phoenix, Arizona, where they actually overlaid their concrete pavements with a form of open graded friction course that happened to have rubber in it. But the point of that was to deaden the noise. And it was actually so successful, the citizens of the city of Phoenix voted themselves a 1-cent sales tax to pay for it, to cover all of their concrete freeways in the city. Yeah, and they were able, the math was, by the decibel measurements, the math was an inch of overlay was a foot of noise barrier in their case. So yeah, it is an issue. We haven't looked at it explicitly. Okay. Okay.
Is DOT implementing that fiber mixture?
No, they are not, and not to my knowledge. Things happen I don't know about. We did that work. That work was sponsored by a company that we were doing. We shared the results with the DOT, and I don't think that they've taken that anywhere. But Virginia has. So Virginia DOT is using fiber in a couple of case studies, small scale studies. Yeah.
So you mentioned several different mixtures. These innovative mixtures, are you just pulling the lever on how much of the different ingredients are mixed into the mixture, or are you pulling in innovative new material?
Yeah, both. Yeah, both. I think the bigger one that we've dealt with, so it depends. The bigger one we've dealt with, and primarily Professor Castoreno, who I talked about at the beginning, has been looking at recycled mixes. So I don't know if you're aware of this. It's a fun fact that I like to share with my students. North Carolina is incredibly permissive with using recycled materials in asphalt mixes. In this state, you can use up to 40% binder replacement, which is roughly 40% recycled mix in new mixes on the surface, which is incredibly permissive when you compare it to surrounding states. And so what she's looking at is, how do we consider that recycled material? And do we consider it as just new rock with asphalt on top? Or do we recognize that when we crush it and when we process it, that we form agglomerations that don't break apart and capture asphalt binder? And so in that case, it's more of the first. We're pulling levers of how much asphalt we're adding, how we recognize the component materials, and so on. But we do look a lot at recycling agents. So these are usually bio-based materials, but they can be paraffinic oils as well. but we'll look at bio-based materials. Much of our work in that space has been kind of applied. So we haven't gotten into the space of designing those materials that are going to be used, except maybe with some polymer modified mixes. And there, again, you have more levers that you. Mm-hmm.
Maybe a few questions. My understanding, you stressed much of this testing the laboratory, measurements in the field, but of course you also clearly define that we have a mechanistic approach to characterization of the behavior of materials. And as I comprehend this, at least, they're highly heterogeneous materials in asphalt you mix. So if you want to go down to a very basic level, you're having to characterize as a time-dependent behavior as well as a spatial variation, individual different materials. It's just incredibly complicated, as I understand it. And these are programs that have been developed here over maybe a few decades. Like Richard Kim was involved, you, Cassie, and then how many different graduate students have been involved in all this?
Oh gosh, I don't know, dozens. I'd have to say.
Right now, for example.
Yeah, so our group right now has, I think, about 15 students total. About 15. 50? No, 15. 15. 150. Yeah, 15. Yeah, I apologize. Yeah.
Well, it's all to me impressive, and as you, I guess, know, I've been involved in modeling several different levels of metals over 50 years, but to me, this is far more complicated than characterizing plastic deformation of metals. Wow. Well, thank you.
Yeah. I'm happy to answer more questions.
And so people are right to say they come up with something later they want to ask about, or
100%.
Email you.
Yeah, easy. I didn't put the email on the slides, but I'm easy enough to find. My profile is public. Yeah.
I think we have one more.
Oh, yeah.
Yeah, please.
I find it interesting that you did work in Virginia.
Mhm.
Is that because Virginia Tech lost out on opportunity, or?
So it's a couple of things. Virginia Tech right now, at least when we started the work, doesn't have a person that's, how to say this carefully, isn't as familiar with doing the mechanistic characterization of material. Their pavement group focuses a lot on pavement management and safety. Now, I think they are hiring or in the process of hiring a person that does do more material characterization. And I suspect that we'll stop working in Virginia on after that. Yeah.
Oh, yes. Wonderful. Good question. So as far as the analysis of the spatial variation under loading, so these are kind of element programs that were developed.
Correct. Yeah. Yeah. And I should say that was not developed by the 3 PIs in the program. That was Murthy Gudati, who was another faculty department, who did the actual implementation of that finite element. Yeah.
Issue with hydroplaning, do you have anything like that? And what is that considered when you come up with a quarter inch of allowing?
Yeah, it's baked into that. The DOT has just recently created, with the help of a consultant, what they call a hydroplaning assessment tool, which allows them to more objectively determine what is the likelihood of that rutting. And so I think what could be possible in the future is even something finer than to say 0.25. That's sort of a baked in kind of implicit number. But that's not the critical number in a location that has a high cross slope and a large longitudinal slope. It's 6 lanes wide. And so tools like that I think are going to allow us to look at this a little bit more discrete way and identify critical rutting at a given location.
that's across longitudinally along the wet facility to avoid areas that are highlight the sag.
Yes, and that's already done to an extent, primarily on the surfacing. Well, I'll tell you a good example. It's not related to the rutting, but it's the interchange at Western Boulevard. The temporary pavement that's out there. I don't know if any of you drive over that or not, but if you do, it was recently shot blasted. So it's not mixed. And it's literally what it sounds like. There's a truck, it shoots metal balls at the surface and vacuums them up and repeats. You can tell because the lane where the lane stripings are is still glossy, because they want to shot blast off the paint stripes. So that's not exactly what you're talking about. But the point is that, yeah, where there are demand needs, we already changed the mix longitude. There's something about the surface characteristics.
So can you change that mix as it's being placed? Can the machinery do that?
No. So you're limited to what the truck quantities can bring, right? So a truck brings, a mix, and then it's put to the paver. That paver takes that same mix. So you have to line up the trucks to get that longitudinal distribution. So it's a logistical challenge, but it's doable. I say that being an academic standing in front of you. So, I don't know what they're going to say, but. Well, if you do have more questions or just curious about things, feel free to let me know. If any of you ever are in Fitzwillard Hall or over there and want to come take a look at the labs, please reach out. I'll be happy to meet with you all, show you around. Thank you all very much.